Vamos a empezar. All right.
Whoa.
14. That's all I
I didn't know
remember
you
from
spoke
this
Spanish.
recordings in Spanish. Yes, I took Spanish. I took AP Spanish.
Ooh.
Yeah. Wait, want to hear a funny story?
Yeah.
Which one? Yeah, not vocal, but speed. You know, that'll keep my attention, right? Length, that's not good. All right. So this slide really has very little to do with today. But I put it in there because I thought it was kind of interesting. It has a tiny bit to do with today. You don't have to write anything about this down. But today we are talking about, we're talking about tangent planes and normal lines. But this was actually from the old textbook. And it was kind of a neat little image. So here's what happens if you've ever played pool, right? So you have a cue ball, and then you have some ball that you're trying to knock into a pocket, right? So the thing I didn't know is that it doesn't matter what direction the cue ball is coming from. It will always move in a direction perpendicular to the point of impact. So if this white ball hits this ball, there's a point there. There's a line tangent to the yellow ball at that point. The line that's perpendicular or normal to that tangent is the direction that the yellow ball is going to move in. So no matter where your cue ball is, what it all is based on the point it hits the yellow ball at. Wherever it hits the yellow ball at, if you were to draw a tangent and then draw a normal to the tangent, that's the direction that the ball is going to move. Which I thought was kind of fun, because today we will do tangents to spheres. And so that's what you're doing here. Is it's really kind of like a tangent plane to a sphere, and then you're going normal to the tangent, which we'll also be able to do. So anyway, kind of fun. So there's no pool problems in your homework, but you know. Okay. All right. So just don't write this down. So what I found was between old book and new book, your old book, the book that you guys did your AP calculus out of, which I call the Larson book because that's the author. So the Larson book does tangent planes much later in the chapter, and so he does them at a kind of a higher level, a more complicated set of problems. And your current book does them much earlier and kind of simplifies them. So what I'm going to do is I'm going to teach you the more complicated way, but I'm also going to show you the way that your book is going to present them. You're like, oh wow, that's so easy. So it's really not that much different, but in order to do it in a slightly more complicated way, you have to understand the difference between writing a multivariable function and writing an equation of a surface. So here's the thing, and you don't have to write this down. I can give you the steps for what you'll see it as soon as we do it. And plus, you don't have to know any of this for homework because they don't ever get into surfaces in this section in your current book. But anyway, so far the majority of our equations in 3-space have been solved for z, right? Z equals f of x, y. For this lesson, instead of writing them in the form z equals f of x, y, we are going to move the z to the other side and have all 3 variables on one side of the equation. So it's the same equation. It's just that it's no longer solved for z. So what happens is you get this f of x, y minus z, and you think of it more as like some big function of all 3 variables instead of a function of 2 variables. So your variables now, you have some surface that's kind of defined in terms of x and y and z. So, okay. All right. Now, the surface, there's a term here. Again, don't have to know this for today, but it will come up later on. When it comes up again, I'll reintroduce this again. So think of the surface described this way as being the level surface of f given by the big F of x, y, z equals 0. So remember that we've talked about level curves, which is what gives us contour mass, which is where you set the function equal to a constant, and then you get all the z values that have that as its constant. Well, this is kind of like when you move the z over, it's going to equal 0. So you're getting all the function values that equal 0. It's called the level curve for the function, but you got to understand that doesn't mean it's flat. So once you're in 3 variables, it's not necessarily flat. So note that when we're finding the level surface of where f of x, y equals a number, this produces a plane because z is a constant. However, once you get to f of x, y, z equals number, the level surface is not necessarily flat. It simply implies a type of equation where a function of 3 variables is equal to a constant. So for example, f of x comma y comma z equals x squared plus y squared plus z squared minus 4. If you were to set that equal to 0, then your equation would be x squared plus y squared plus z squared equals 4, which is just a sphere of radius 2. So anyway, so just because you have like your equation equal constant doesn't mean it's flat. Once you're in 3 variables, you get anything, so it's called a surface equation. Anyway, all that being said, all that means is today in a lot of the problems I'm going to show you, the functions aren't going to be solved for z. That's all I'm saying. Like it's not, that's all, like all this is just to tell you we aren't going to solve them all for z. Okay. Okay, so today we're going to learn how to write an equation of a plane tangent to a surface. I also mentioned normal lines, but I don't think we're going to do normal lines. It's definitely, they're not in your homework at all, and we need to start differentials today too. All right, so let S be some surface given by some surface function, f of x, y, z equals 0, and let P be some point on S. I don't know if I want you to write this whole thing down. It looks huge. Look at that. Look at this giant equation of a plane, right? Do you guys remember how to do an equation of a plane back when we were doing it? We did this in the very first chapter, right? So when we did the equation of the plane in the very first chapter, we needed, when we were just talking about vectors, we needed a point and we needed a direction vector, right? And that gave us our equation. And oh, and that direction vector for when you're talking about a plane, the direction vector has to be normal to the plane, right? Okay, and so the equation of the plane back in the chapter 12 was the x part of the direction vector times x minus the x value of the point plus the y part of the direction vector times y minus the y value of the point plus the z part of the direction vector times z minus the z value of the point, right? All this is saying in order to get, when you're in a multivariable function, in order to get your normal vector, it's really your partial with respect to x with the point plugged in, whatever that number is, right? It's the slope at that point. Partial x times x minus x sub 0 plus partial y times y minus y sub 0 plus partial z times z minus z sub 0. It's exactly the same as what you did in chapter 12. It's just written in a great big giant long way. And the difference now is that in order to get your normal vector, you have to do partial derivatives. Now, why the partial derivatives give you the normal vector? This is why it's throwing me off why we're doing this now and not after we learn gradients. Because the whole point of this is that this, and this together make the gradient, form the gradient vector, which is this vector that's normal to the curve at that point. So, anyway, well, I don't want to skip it. We're going to follow the new book. So, we're not skipping it. Okay. So, anyway, so just know it's just partials times x minus points. Each partial times that variable minus the point of that variable. All right, so the plane through P contains two. So, the way that your book describes it, so our old book used to say that the plane that's tangent to the curve is the plane that passes through a point and contains the gradient vector, right, or is normal to the gradient vector. Now this book says, instead of talking about the gradient vector, they say if partial x and partial y, like say you have like partial x and partial y, if both partial x and partial y are on the plane, then the plane is tangent to, or the plane is normal to, tangent to the curve. Keep on getting normal and tangent. So if partial x and partial y are on the plane, then the plane ends up being tangent to the curve. And how does that work? Anyway, you'd have to see.
I thought you could like show is that not what the drawing is?
Show an equation how what?
Like, I thought you couldn't like draw an equation in 4 dimensions, right?
That's an equation in 3 dimensions, but the equation has been presented in a surface equation form. All they did was move the z to the other side.
Okay.
Yeah. So we can solve the equations for z. You're right. So it's really 3 dimensions.
Okay.
You can solve the equations for z, all the ones I'm going to show you. It's just a lot of them, it's easier if you don't. It's kind of like doing implicit versus regular differentiation. Okay. So anyway, let's walk through a problem together, and then I will give you one to try. So we're going to start by finding the equation of the plane tangent to the hyperboloid given by z squared minus 2x squared minus 2y squared equals 12 at the point 1, negative 1, 4. Now, I haven't taught you about how to write the equation of a normal line, a line normal to the hyperboloid at the same point, but we're going to see if we can figure that one out. So the first thing that you're going to need in order to find the equation of the plane is you're going to need to find partial x, partial y, and partial z. So go ahead and find your partial x, partial y, and partial z. Think of this whole big thing like f of x, y, z, right, as z squared minus 2x squared minus 2y squared minus, the 12 is irrelevant. It's going to go to 0 no matter what. But technically you move everything to one side and you call that whole thing big F. And then what you're finding is partial x, so big F sub x, and then partial y, and then partial z, right? So find partial x, partial y, and partial z. Am I confusing you? Do you want me to help you with partial x?
No, I'm just confused as to like, so is this like in 4 dimensions now? Or
No, we're in 3 dimensions. We're just writing it differently.
No, but like, I mean, what is it? Isn't there like z squared, x squared, y squared, and dimensions though?
This is our original equation.
Right, so aren't there like 2 different variables in the original equation?
Yeah, but if we could solve this for z.
Oh, wait, never mind, I'm an idiot.
No, you're not an idiot. There's
Yeah,
3 variables. That's 1 for each dimension, right?
Yeah. Sorry, I thought we were, okay, never mind.
Yeah.
I don't know what I was thinking.
No, it's okay.
It
This
feels
is
like f of x, y, z should be a variable. That's
right, right. And that's the thing that gets kind of weird about surface equations, is understanding that you're right. Big F of x, y, z feels like that's the output variable,
It's just 0.
but it's just equal to 0.
Got it.
Oh, see, and here, my solutions, ignore my solutions, I'm going to write it over here. Okay. So, big F sub x, so we would get negative 4x, right? Big F sub y would be negative 4y. And then what's big F sub z? 2z. So what we need now is we need each of these at that point. So you need big F sub x at the point. So what is the component of our normal vector in the x direction? Negative 4. Then big F sub y at the point would be positive 4. and then big F sub z at the point would be 8. So this is kind of like the normal vector for our plane. Would be negative 4, 4, 8. Okay. All right. When you look at the smart boards, you're going to see me use this little upside down triangle thing. Just don't let it throw you off. So it's a shorthand way of writing your partial x, partial y, partial z. Just it's like a shorthand. It's a vector form. This is actually, I mean, I'm giving you a preview, but this has a name. It's called the gradient, and all it is partial x, partial y, partial z. Okay. So anyway, so you do it at the point. You get negative 4, 4, 8, and then to write your equation, it's just going to be negative 4 times x minus 1 plus 4 times y plus 1 times 8 times z minus 4, right? It's nothing different than what you've done before. It just feels a little bit different. Am I going too fast? You tell me if I'm going too fast.
Yeah. So like when you're like negative 2, negative 2, go vector, and use that line.
What's your question?
I'll put a second line like that in front of the
Oh, when we write the equation of the line normal at the same point?
Or do you like the cross product?
Mm-mm. What do you need to write it? First of all, this vector right here, these three numbers right here, those form the vector that's normal to the surface. And so for the line, we just need that same vector, right?
Yeah.
And now you're just writing it as a line because this vector now would be on the line normal to the plane.
Right. Yeah.
Yeah, I don't know what I've got that. Oh, that's just me cleaning that up.
Like negative 4 plus 1.
There might be time for a quiz.
4t minus 1.
Is this all we're learning, guys?
No, there's more.
Okay.
Oh.
Okay, so if we wanted to write the equation of the line, which your book is never going to ask you for until like, later. So anyway, so the equation of the line, so this would be our direction vector for the line. And then, I don't know what did I ask you? I didn't ask you for any, I didn't ask you for a format. I just said find the equation of the line. So you could say x equals negative 4t plus 1, y equals 4t minus 1, and z equals 8t plus 4, right? Now I do a slope point. Line. Right. And then that's just me writing them as symmetric, but it's the same thing. Yes, Zach?
So why do it do that? What was the point of doing the negative 4 times x minus 1 plus 4 times y plus 1?
This is a plane. This is an equation of a plane, right? This is an equation. That's an equation of a line. The plane is tangent to the surface. So whatever this surface looks like, it's some hyperboloid. There is no way on earth I'm drawing a hyperboloid freehand, but somehow you have some hyperboloid that's either going this way or this way. I don't know. Since the z squared is positive, do you think it's going this way? Like there's my hyperbola. I have no idea, right?
Sure, let's just say it.
Okay, let's just say it is, right? So anyway, so you pick some point that is whatever it was, 1, negative 1, 4, right? So 1, negative 1, 4. So let's just, no idea where that point is. Let's just pretend that point's right there, right? This is the worst. I really should just do this in Grapher. there's some plane tangent to the surface at that point. I really need to do this in Grapher. I'm so bad at 3D drawing. So this is the equation of that plane, and then there's some line that's perpendicular to the surface. That's the equation of the line. Yes, Anna.
So is the plane, is that like on like tangent to that surface or just
Tangent to the surface. Do you want me to do it in Grapher? Then you can see it nicely?
yes?
Yes? Okay. All right. So here, let me write them down. All right. So our equation, z squared minus 2x squared minus 2y squared. Where is everyone going? Come back here.
Oh yeah.
Yeah, but you can't have like 4 people take one bathroom. Already done.
You just like stand and scare them away from
Okay, so this is our surface. Okay, and then this negative 4 times x minus 1 is 4 times y plus 1, 8 times z minus 4. That's our plane. And then our line is x equals negative 4t plus 1, y equals 4t minus 1, z equals 8t plus 4. All right. I'm up for some graphing fun. So let's see. All right. One person out at a time, gentlemen. Okay. All right. So just so you know, even though it says z equals, you can kill that and just type in your equation however you have it. Z squared minus 2x squared minus 2y squared equals 12. Okay, so there's my hyperboloid. All right, hey, I did it pretty well, right? Come on. Okay, so now let me add. So then this one, negative 4 times x minus 1 plus 4 times y plus 1 plus 8 times z minus 4 equals 0. All right, now, okay, so there's, like, you can kind of see where the point of tangency is, and that this plane is tangent at that point. So, like, you can kind of see that that's where the point was, and that this plane is tangent at that point. All right, and then I'm going to show you the normal line. Okay. All right, so x equals negative 4t plus 1. Y equals 4t minus 1. And z equals 8t plus 4. Now, I'm not sure what values of t to use. Well, I need to go maybe negative 10 to 10. There we go. And so here's so you can see this point right here. That's the point that we're talking about. That's the point, whatever it was, like negative 1, 1, negative 4. And then, so you could see it coming through the tangent plane. So this line that we just found is normal to the surface at that point, and the plane is tangent to the surface at that point. Does that help? No? Yes? I can't tell. You're all sitting and staring. Yes. Through that point. Laura, what was your question? You sure?
Yeah.
Here, wait. I'll zoom in a little. Oh, wait. That didn't help at all. We've gone into abstract mode.
Okay, all right, that's enough of that. Let's move on.
Miss Price?
Yes.
Is the point given always going to be on the surface of the
Yeah, it has to be on the surface, otherwise it's just silly. Yep. Good question. Okay, all right, guys, give it a try. Find the equation of the plane, tangent to the surface. No, do this on paper. I'll give you one to do on your whiteboards in a minute. Do this on paper. So, all right, do it on your whiteboards. Okay, find the equation of the plane, tangent to the surface, x equals y times 2z minus 3 at the point 4, 4, 2. Then find the symmetric equations of the line normal to the surface at the same point.
Did you work the problem? Oh, that's fine. Paper's fine. All right. So first thing that I did is I moved everything to one side. I just subtracted the x, but you could have subtracted the other stuff. You know, it doesn't matter. You're going to get the same partials, just opposite signs, and a scalar multiple is fine. So anyway, so my partial x was -1. My partial y was 2z minus 3, and my partial z was 2y, which I'm seeing that around on the boards, so that's good. Yeah, some with opposite signs for me, and that's fine. Yep. Yeah. Okay, so then you plug in your numbers. So I had -1, 1, 8. If you had 1, -1, -8, that's fine. So we match. Yeah, we're fine. Everyone's got the same thing or a negative scalar of the same thing. All right, so the equation of the tangent plane. So negative times x minus 4 plus y minus 4 plus 8 times z minus 2 equals 0. Yeah, gorgeous. That's good. Good. Any questions on the tangent plane? All right, and then the normal line, same thing, just written as a linear equation, right? But same direction vector, same point. Let's see. Yeah, that's this. No, wait, something happened. Did I mess up the sign? No. Okay. So, but you have negative x minus 4, so you gotta be careful. One of those is wrong. The middle one's right, and then the bottom one should be a z minus 2. Is that a 2? Anyway, there's a couple little mistakes in the math when you wrote them as symmetric. But I like the curvy equal sign. Okay. All right. Good. Yeah, these look good. I like them. All right. Okay. Notes. So, your new book. We're going to do one that's going to look more like your homework tonight. Because your homework tonight's actually easier than what we've been doing, even though what we've been doing hasn't been very hard. So, your new book has every single equation solved for z. Now, when every single equation is solved for z, what that means is if you move everything to the same side as the z, partial z is always going to be 1, right? Because everything, you just have a z, everything else goes to 0, and the derivative of z with respect to z is just 1. So what they're doing is they're giving you every single problem already solved for z, and they're saying that since the slope of the partial z will always be 1, they write the equation where you don't, they speak about it as though you don't need a slope in front of the z. So they do z minus z sub 0 equals, and then they do partial x with its stuff and partial y with its stuff. It's kind of it's an approach I haven't seen. So I don't want to criticize too much because it's just because it's not what I'm used to. It's just different. So anyway, so we're going to walk through one that you'll see in your book tonight. Honestly, if you do it the way we've been doing it and enter it the way that we've been writing them out, that's fine. The book accepts it because they don't care how you enter your equations, whether they're solved for z or not solved for z. So if you want to just keep doing it the way we've been doing it, you'll get them right and life will be fine. Okay? I'm going to show you this just so you understand what the book is doing. So the book is just saying, hey, z sub x. So z sub x for this would be what? 2y. And then z sub y would be
-2x plus 2y.
plus 2y.
So if we have z sub x at the point 1, 2, negative 4, we get 2 minus 4, we get negative 2. And then z sub y at the point 1, 2, negative 4, so is positive 2. Thank you. All right. So then the way that they are writing out the answer is they're saying z minus the z coordinate equals, and then they're going negative 2 times x minus the x value plus 2 times y minus the y value. So they're doing it like that. Because the slope for the z will always be 1. It's just what they're doing. Because if you have it solve for z, right? If you have it solve for z, then there's no coefficients or anything, so it's just going to always go to 1. Yeah. So it's kind of a weird way to do it, but that's what they do. So it's their way of getting around, like having you introducing this topic before you've learned the gradient. So it's, anyway. So that's what they're doing. If that's, you can do that. That's fine. Because you'll get them all right. It's up to you. Or you can do them by moving the z over and doing it the other way. It's really potato. It's not really much work either way. So. Okay, last topic of the day. I am going to have us do a little bit of the beginning of Monday's lesson today as well. So we're going to do this. Then I'm going to switch to Monday's lesson. I'm still going to save about 20 minutes for quiz time, but Monday's lesson is huge, so I want to try to see if we can get through a little bit of it today. All right, so differentials. In this lesson, all you have to be able to do is compute this with no explanation as to what a differential is, how it works, or why we use it. Monday is when you learn what a differential is, how it works, and why we use it, and Monday is major applications. But this is just a very quick nuts and bolts of what a differential is. So if it's solved for z, if you have z equals f of xy, then a lot of books call it, and I'm telling you online too, I see online sources call it just differential, and online sources call it the total differential. So just know you might see either one if you're researching. But anyway, so dz, not del z, dz equals partial z partial x dx plus partial z partial y dy. So in other words, f sub x dx plus f sub y dy. If you had z equals f of wxy, it'd be the same thing with partial z partial w plus dw plus. You just add as many variables as you want. All right. We are going to find the differential for the function z equals 2x sine y minus 3x squared y squared. It's just more practice with partials. So take a minute, see if you can figure out how you would write the differential for z equals 2x sine y. Okay. All right, so your partial x. So partial x would be 2 sine y minus 6xy squared, right? Did I do that? Yeah. Okay. Everyone get that for partial x? Partial y. So you have 2x cosine y minus 6x squared y. All right. And then your differential, you just take your partials and you're just multiplying them by the dx and the dy. That's it? Yeah, that's all you do.
What is the dx?
That's what we're doing on Monday, but I'm going to start showing it to you today. Okay? Your homework tonight is equations of tangent planes, right? And it's just an empty box, and you can put the equation in any format you want. And then the differentials, literally, it has dz equals, and then it has an empty box with dx next to it and an empty box with dy next to it. Yeah, so you're going to like your homework tonight. You'll be done in 10 minutes. So anyway, okay. So I am going to keep going, though, because Monday's lesson's so big, and I want to give us a little intro to it. Oh, wait, let me export this real quick.
All you have to do is
All right.
Oh, right.
Okay, so I want you to take a minute at your desks, not on the boards, just at your desks, and I want you to do the warm-up. So here's our warm-up. This is going to get us into the world of what differentials actually are. All right, do them on the boards. All right. So the Fall to Pieces Quilting Company produces fabric squares to use for patchwork quilts. The squares are supposed to have a side length of 4 inches, and the company promises that the length will never be off by more than 0.01 inches. What is the worst possible scenario for error in the area of their squares? So ideally, we want the area of each square to be 4 squared or 16 square inches, right? But no machine is perfect when it's cut, especially when it's cutting something like fabric, right? It's never going to be exactly 4 by exactly 4. So there's always error when you are manufacturing something. The government actually controls for different types of products how much error is allowed in packaging, right, or in production of the product. So for this one, the company promises that the error in the length of a side will never be more than 0.01. They don't say if it's going to be higher or lower. Could be either way, right? So anyway, I just did the higher. 4.01 squared is 16.0801. So worst possible scenario would be that the square is off by an area of 0.0801. Now this group did the under if it went to 3.99, and then the area was off by 0.0799. Now, what's going to happen in this class is rather than having to do both the positive and the negative, the higher error and the lower error, we're just going to do the higher and say it's like roughly plus or minus because they're close. They're always close. So we're not going to spend a lot of time doing getting all those decimals. We're usually just going to go up and call it good. So anyway, all right. So today meaning Monday, we're doing 14.4b, which is all on applications of differentials.
how much are we doing today?
We're going to stop at 1/4 and I'm going to give you a quiz. Yeah, today's the 16th. I didn't hear what you said, but today's the 16th. Don't you ever worry about that, hurting you in some way?
If it was like this.
Yes.
Yeah, but it's like this, so it's fine. That's fine.
All right, what did we skip last year? Oh, yes, Zach. No, just keep going. I don't care. Okay, so what did we skip last year? The next 9 slides are actually from section 3.9. We never did section 3.9 last year. So, yeah. So it's not trig sum. Okay, 3.9 is actually differentials, which we pretty much skipped. We covered them I covered them in one example in literally like 40 seconds and then moved on. So yeah, because it's not an AP topic. You don't write this down. This is just to lead you into where we're going, okay? So this is kind of the two-dimensional version of differentials, and then we're going to open it to the three-dimensional version of differentials. So I'm hoping to cover the two-dimensional version today, and then Monday we can start right in with the three-dimensional version of differentials. All right, so if we had to write the equation of the line tangent to f at the point C, f of c. So you'd have y minus f of c equals f prime of c times x minus c, right? Everyone comfortable with the equation of a tangent? Point, slope, right? Okay, good. X minus c is denoted as delta x. Y minus f of c is denoted as delta y. So we could actually rewrite the equation as delta y equals f prime of c times delta x. Change in y equals f prime of c times change in x. Well, gosh, you know, when delta x is super small, approaching 0, we call delta x dx, which is called the differential of x. So just think about it. If you divide by delta x, right, you get f prime of c equals delta y over delta x. Really, if delta x, you want that delta x to be super small. So anyway. All right, so here's the thing. Delta x is literally the change in x, and delta y is literally the change in y. Is this me drawing stuff? Yeah. So if I'm on a curve, the red thing is the curve, and I'm going from here to here. My delta x, that's the difference between the two x values, and my delta y is the difference between the two y values. As we discovered in the warm-up, just for the easiest, simplest equation like area, computing the error between what we found like with optimal area and what we found with a possible area with a side length that's slightly off is a little bit of a pain. And so you end up with a lot of arithmetic and a lot of calculations to saying, hey, if my input is off by 0.01, what's my output off by? Essentially, right? So you're thinking of delta x as like the difference between what you want and the error, right? The x with the error in it. And then the delta y is how does the output get affected by that? So what we have found is that since delta y, delta x represents slope, okay, that's just me talking you through this. So what we found in math is as long as that the error is pretty small, we can use dy as an approximation for delta y. So we're actually, delta y is actually the true difference, but dy is an approximation of the difference using slope of the tangent instead of slope of the secant. Okay? You guys are waiting, like you're about to say time is up, like you don't want to hear this anymore. So,
Just do it.
okay, all right, we'll start into this on Monday.